Hi everyone, I'm Wenlun Zhang from Keio University. I'm pleased to share our recent work on HCPTQ, accurate and hardware compatible post-training quantization for segment anything model. The segment anything model, SAM, is a powerful foundation model designed for profitable segmentation. It achieves outstanding results on many downstream tasks, but deploying it in practice is challenging due to its massive storage needs and high computational costs. Post-training quantization (PDQ) provides an effective way to compress the model while avoiding expensive retraining. However, applying PDQ to SAM is not straightforward. We observed two unique challenges during quantization. The first one comes from the post-glue activations, which follow a heavy-tailed and skewed distribution. This irregularity makes it hard to assign quantization grids. Second, the query, key, value, and linear 1 projections exhibit substantial interchannel variation. This variation makes it difficult to decide the proper quantization scales and zero points. To overcome these challenges, we introduced AHCPTQ, which brings together two complementary techniques. Let's first consider the post-glue activations. The uniform quantizer works well for large values but lacks precision for small ones. On the other hand, the log2 quantizer captures small value accurately but cannot represent large value effectively. To solve this, we designed the hybrid log uniform quantizer, or HLUQ. It applies log2 quantization to the dense small activations and the uniform quantization to the sparse large activations. This hybrid approach ensures accurate representation across the entire range while keeping compatibility with efficient hardware implementation. For problem of interchannel variation, per-channel quantization is often used to improve accuracy. However, it comes at the cost of more quantization parameters and higher hardware complexity. Our approach, called channel-aware grouping, or CAG, progressively cluster channels during reconstruction. By letting channels in the same group share quantization parameters, CAG significantly reduces parameter overhead while still preserving accuracy. To test the HCPTQ in practice, we built an FPGA accelerator together with the quantization method. For HLUQ, we wrote the weights and activations using MSB, sending them either to the multiplier lanes or to the bit shift lanes. For CAG, we keep only a small set of grouped quantization parameters on the FPGA and add reorder logic directly into the buffer. This way, CAG maintains accuracy close to per-channel quantization while cutting parameter registers by 99%. As a result, our 4-bit HCPTQ accelerator delivers an 8.64x energy efficiency gain and a 7.89x speedup over floating point baseline. We tested the HCPTQ on the COCO dataset for instance segmentation with 4 types of detectors. Across all settings, our method outperformed the baselines, set a new state-of-the-art, and crucially remains effective under 4-bit quantization. Here we show the visual results for 4-bit quantization of SAM-H. As you can see, HCPTQ produces segmentation masks that are very similar to the floating point model, while still keeping the fine structural details and sharp object boundaries. This highlights its effectiveness under low-bit quantization. Thank you for your attention. More details can be found in our paper and code, available on arXiv and GitHub.